In this video, we're going to talk about assessing normality. So remember, a normally distributed graph is roughly symmetric, single-peaked, and bell-shaped. And anything that's not normal is called non-normal. Fancy that. So this dot plot is not normal. It's not really bell-shaped. It's single-peaked, but it's definitely not symmetric because we've got this tail over here. So anything that's skewed is non-normal. Also, just a little reminder, never say that a distribution of quantitative data is normal. Real-world data, is not perfect, so it has departures from a typical normal distribution. So you can say that the distribution is approximately normal or roughly normal, just like we say it's roughly symmetric. So that would mean that even if a graph looks roughly symmetric, it doesn't mean that it is. So this dot plot looks roughly symmetric. So something that you could do algebraically is take the mean and the standard deviation and our 68, 95, 99.7 rule, I mean, that just rolls off the tongue, doesn't it? And figure out algebraically, well, does the first standard deviation contain values that are about 68% of the distribution? So in this example, we would take the mean, 106.883. We would add and subtract one standard deviation. So that's 1 times the standard deviation. And you get approximately from 87 to about 126. So that's 63 out of 77 values in this dot plot or in the data distribution. And that covers roughly 81.8%. Now that to me tells me that is not a normal distribution because that's very far away from 68. Even though 92 is close to 95 and 100 is very close to 99.7, I would say that this is not a normally distributed data distribution. So now let's work through an example together. This one's called Are IQ Scores Normally Distributed? Let's assess normality here. Now let's put aside the controversy of, IQ tests and that whole thing. And let's look at the problem. Many people believe that the distribution of IQ scores follow a normal distribution. Is that really the case? To find out, researchers obtained the IQ scores of 60 randomly selected 5th grade students from one school. Here are all the data. Woo! And here is a histogram of that data and the analysis. So let's figure out, is this distribution approximately normal? And of course, we're going to justify our answer based on the graph and the 68, 95, 99.7 rule. First thing I'm going to do, just like we did in that previous slide with that example, we're going to take the mean and we're going to add plus or minus 1 standard deviation, 2 standard deviations, and 3 and figure out, is this normally distributed? So let me show you what I did with the first standard deviation from the mean. You take the mean, 114.983, you add and subtract 1 standard deviation, and that's going to be 1 times our 14.801, and we get a range of 100.182 to 129.784. So what you could do is you could take this histogram, or you could take your data points. I prefer the data values themselves because I make less mistakes that way. And I'm going to count from 100.182 to 129.784. So this 100 doesn't count because it's less than 0.182. So all of these highlighted values up to 128 fall within 1 standard deviation. I counted them up. That's 41 out of 60 data points, and that's 68.3%. So that really fits nicely in the first part of that 68, 95, 99.7 rule. So let's work out the rest and see if this is normally distributed. So here we go. The mean plus or minus 2 standard deviations is actually 57 out of the 60 scores. I tried to highlight that in blue here. It's a highlighted mess. That accounts for 95% of the scores. And then 3 standard deviations out account for all of the scores. So all 60 fall within 3 standard deviations. So that makes it 100%. So with this 68.3 being very close to 68, this 95 being smack dab on, and this 100% being very close to 99.7, we can say that this distribution is approximately normal. Thanks, algebra. Something that makes looking at whether a distribution is normally distributed is something called a normal probability plot. So that's a scatter plot of the ordered pair. of a data value and the expected z-score for each of the individuals in a quantitative data set. That is, the x-coordinate of each point is the actual data value, so for example, that an IQ score, and the y-coordinate is the expected z-score corresponding to the percentile of that data value in a standard normal distribution. So remember that normal distribution, that mean becomes 0, and each standard deviation becomes 1, -1, 2, -2, etc. So x-coordinate, actual data point, y-coordinate, z-score to that percentile within the distribution. And just a note on software here, which I will show you towards the end of the video, how to use your calculator to make a plot of normal data, which is lovely. So some software puts the data values on the horizontal axis and the z-scores on the vertical axis, while other software does the reverse. The TI-83 and 84 gives you both options, and we prefer the data values on the horizontal axis. It's just consistent with the other types of graphs we've made and will continue to make. So no matter how you make your scatter plot, there are 3 different ideas or 3 different things to kind of look for. The first is if you have your distribution, like our IQ scores in that last example, if you went to make a scatter plot of that data where the x-axis again is the raw data point, so that's IQ score, and then the y-axis is our expected z-score compared to the rest of the data, you'll create something that is linear. So we know that this distribution was approximately normal, so an approximately normal scatter plot is going to create a linear form. So next up is something that is definitely skewed. So what we have here is a right-skewed dot plot, where the values over here on our scatter plot are the raw data values, and then the z-score is over here. So anything that is skewed is going to create a curved scatter plot. And lastly, here's something that looks approximately normal or roughly symmetric. We've got something that looks roughly symmetric, roughly bell-shaped, right? So when you go to make the scatter plot, where you have the raw data on the x-axis and the expected z-score on the y-axis, it's not quite linear. It wants to be, it looks like it's really close, but it's not quite. So that means that this dot plot is not approximately normal, because its scatter plot creates this different kind of nonlinear form. So what should you look out for? Well, if you look at the points on our normal probability plot, so that's the scatter plot, where the x-axis is the data value and the y-axis is the expected z-score, you look for something that looks like a straight line. That would mean that it's approximately normally distributed. Now, each of these 3 are roughly linear, so we would say that they would be approximately normally distributed. Remember, real-world data is not perfect, and it will not be perfectly normally distributed unless you cherry-pick your data points, and then that's not really random, now is it? So you look for something that is roughly linear. Anything that's nonlinear indicates that it is a non-normal distribution. So now let's look at an example where we can interpret normal probability plots, aka scatter plots. So this one's called How Normal Are Survival Times? Now we're jumping from humans to guinea pigs. So the problem says researchers recorded the survival times in days of 72 guinea pigs after they were injected with infectious bacteria in a medical experiment. A normal probability plot of the data is shown. Use the graph, ta-da, to determine if the distribution of survival times is approximately normal. Now, I don't know about you, but that doesn't look linear. So we could tell right away that that's going to be a curve. So thank goodness for these graphs, because it makes it pretty quick and easy to say that the normal probability plot is curved. Therefore, that indicates the distribution of survival time for these 72 guinea pigs is not approximately normal. And as promised, here's how you would make a normal probability plot on your TI-83 or 84. So whatever your data is, you would go to Stat and you would go to Edit Your List. You can put it under whatever list you want, especially if you've got other lists in there, but if you don't have anything, it goes under L1. Just keep track of what list you're putting that data in. And so next, what you would do is you would set up a normal probability plot in the statistics plot menu. So when you go to second y equals, that brings you to stat plot. You're going to hit enter and go to the first stat plot. You want to turn that on. So you make sure it's highlighting stat plot 1. It's on. The type is going to be this last one. So that's going to make a normal probability plot for you. Make sure this data list corresponds to whatever list you entered in your data values. You want your data axis to be X. You want your mark, I mean, you can make it anything. Doesn't matter. And if you've got a color option, hey, go wild. So from there, you're ready to look at your graph. So when you hit graph, because you want to do that, if you don't see any of the plots or if you only see part of it or none of it, you would go to zoom and then go down to zoom stat, which is number 9 on my TI-84. May be different for you. But if you do zoom stat, it should bring you to something that looks like this. So this data that we entered, or at least that's screenshotted here, is from those IQ scores from the beginning of this video. So the interpretation here would say that this normal probability plot is quite linear-esque, right? So that confirms our earlier belief that the distribution of IQ scores is approximately normal. Gotta love it. All right, and that's gonna do it for this video. Thanks for watching.